Okay, so in this part 2, I'm going to go over a couple problems which were left. Anything which is kind of common, like the dehydration, if I'm using one substrate, please work it out on your own. For another substrate, it really doesn't matter if it's the same reaction. But anyway, notice in the first problem, you have been given that you have a ketone and it's supposed to go to an alcohol and a secondary alcohol. So that's telling you that it's a reduction reaction. So any reducing agent such as sodium borohydride in THF as the solvent, or lithium aluminum hydride, LiAlH4 with THF, those will be great starting points. POCl3 is a dehydrating agent, so it's supposed to remove OH and one of the beta hydrogens, either from the right hand side or from the left hand side, one or the other. So there are two possibilities. Upon dehydration, you can get either this alkene or you could get the other alkene, and hopefully you can recognize that this is going to be your major product in accordance with the Zaitsev rule that most substituted alkenes are more stable. Let's take a look at the second one. This is just the opposite of what you saw earlier. You're given a secondary alcohol which is getting converted into a ketone, so that's some kind of an oxidation reaction. And so if you use something like PCC and dichloromethane, that will be a good reagent for this. Once you have your carbonyl compound in place, treatment with HCN and a base used is usually ammonia, is going to give you the cyanohydrin, much the same way we discussed in class. And the next one is that you are given specifically formaldehyde and CH3MGBr. Realize the negative end is going to attack the electrophilic carbon. That's going to give you the oxygen with the magnesium. And upon hydrolysis, when we carry out the hydrolysis in the second step, it gives you OMGBr, and that upon hydrolysis is going to give you the primary alcohol, so you will end up with ethanol. That with chromic oxide, CrO3, and acid is what is Jones reagent. And so that's going to simply oxidize the alcohol all the way to the carboxylic acid. If that is clear, let's take an idea. Let's go over the dehydration of 1-methyl cyclohexanol using POCl3 and pyridine. So let's take a look at that. The question is that you have to begin with 1-methyl cyclohexanol. That's this molecule. And it's supposed to go through some kind of a dehydration process. That means water has to be removed when you're treating this with POCl3, and pyridine is the base that you're using. Realize you can use something like triethylamine for this process, but in this case we have used pyridine anyway. Between the POCl3, phosphorus is the most electron deficient, or rather least electronegative. So the lone pair of electrons on oxygen is going to attack the phosphorus. Electrons will move on top of oxygen. You're going to get oxygen right now will have a positive charge. It's attacking phosphorus. That will have the negative with the 3 Cls. The negative charge will come back in, the Cl is going to leave. In the meantime, the pyridine can pick up the proton for the oxygen, so that we can neutralize that and take it further. And so hopefully you can see that oxygen being electronegative is going to pull the electrons towards itself, so the carbon-oxygen bond is going to move, and a base such as, or the conjugate base, the Cl negative or pyridine, you can use either of the two, it's an equilibrium, is going to pull that proton off through a beta elimination reaction, and you're going to end up with an alkene like that, plus phosphorus, double bond oxygen, O negative, and the 2 Cls. If one of these comes back, another Cl can leave. Understand that there's two possibilities, because if you think about the alpha position, there are really three beta positions here. So you can have a double bond in between. You can have a double bond on the other direction. These two are exactly the same. You can also have the double bond if you include the methyl group. So something like that, but that will have to be your minor product in this particular situation. Okay, let's discuss another problem. We actually ran the same problem in class um, some couple of weeks ago. You're given an alcohol and we are treating that with PBr3 and then further with sodium methoxide. So understand that the PBr3 is a brominating agent. It's used to essentially get rid of the alcohol and put in the bromine. And so in this case, the incoming bromine is going to go through an SN2 reaction. So your product should be reflective of the inversion of the configuration. Understand that nothing happens to the methyl group, it's just that the bromine comes from the backside. That's the first SN2 I mean. And now you have another nucleophile in the form of methoxide. That will be another SN2 reaction that will be occurring in this particular situation. And this methoxide is going to attack from top. So you're going to end up with an OMe or OCH3 as your final product pointing towards you. Now, if you did do the same reaction, but now first treating it with a tosyl chloride, in that case, realize it's the OH which is participating in the reaction, and it doesn't quite actually go through a CO bond cleavage, but rather an OH bond cleavage. So you get OTS. This is TSCl, this entire part up until the SO2 is the tosyl group. And now if you treat it with the base, that's the SN2 reaction right there, and it's going to give you the benzene ring and then the methyl group, and of course now the incoming OMe is going to come from the back direction, and so these are going to point in the backward direction. Having discussed that, let's take a look at, we have a ketone, it's forming a secondary alcohol, so hopefully you can see it's some kind of a reduction reaction. So let's use lithium aluminum hydride, THF. In this case, you can use sodium borohydride in this case as well. That when subjected with PBr3, like I said, that is a brominating agent. It's going to get rid of the OH and give you the Br. If nothing is mentioned in terms of the direction it's pointing, just keep that racemic, so keep that on a solid line. But otherwise, like I discussed, you would want to show the SN2 reaction if the stereochemistry is shown clearly. Now, the secondary alcohol that we have gotten, we are subjecting that to PCC conditions. Understand PCC is an oxidizing agent. So again, we would basically be converting this secondary alcohol into the ketone. So these two are similar structures as expected. We are subjecting that to this ketone, the newly formed ketone, to essentially acetal formation, and I know that it's an acetal because not a hemiacetal, because I used two equivalents of the same. So my product, hopefully you can see, is going to look like an OET on both sides. On the other hand, if you try to do an HCN reaction, and usually we do require a weak base such as ammonia for that, in that case you're going to end up with an OH as well as a CN. All right. And then I had another problem in which it's a reduction reaction that is being carried on some molecule. We don't know what that molecule is, and that gives us two alcohols. Recall that it's basically esters which will do this, but two kinds of esters can essentially give rise to these two alcohols. One would be if I take propyl acetate. So I have a propanol, and so if I switch the color, upon reduction, it's this bond which will get cleaved, and the aldehyde will eventually get reduced to the ethanol, and the remainder will give you propanol. Alternatively, another option for this would be if you start with propyl group and ethyl group here. So in that case, you will get ethanol again, and this part is going to give you the propanol. So two possible answers for this are propyl acetate and ethyl propanoate, one or the other. Now, understand that if you are treating, let's say, ethanol to cold conditions with dichromate, you're going to get the aldehyde, and that upon treatment with the Grignard reagent is going to, so if we are adding 4 carbon chain, it's going to give you a secondary alcohol, and it's going to 1, 2, 3, 4 extend the chain length by 4 carbon atoms. On the other hand, if you're looking at propanol with thionyl chloride, since that is a chlorinating agent, it's going to simply give me the primary alkyl halide as the final product. So realize a couple of things here. You can generate from the alcohol to the alkyl halide. You can use PBr3, PCl5, SOCl2, depending on the halogen atom. That is the halogen atom that gets incorporated in here. On the other hand, if you have things like POCl3 or H2SO4 heat, those are dehydrating or elimination conditions. Conversion of alcohol to alkyl halide, that's a substitution reaction conditions. Okay, I think this basically covers majority of the questions that were asked in the 4 different sets for the take-home quiz. So good luck. Should you have any questions, feel free to email me. All right, see you Tuesday.